I'll make a start. Good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast, and good evening to anyone who's joined us from Europe. Thank you for joining this, our second of what is going to plan to be a regular series of seminars on pumping topics. This one will last about 30 minutes, and that will give us some time at the end for a Q&A session. Now, we are deliberately steering away from product presentations and towards educational content. We believe this is very important in the new world order of so many engineers working from home, which makes in-workplace training that much more difficult. Having said which, I hope you'll forgive me one or two slides to remind you of who we are and what we do. We are Rohr Pumpen, and we are truly a global company these days. We have 65 years of experience. We have manufacturing facilities in 10 countries and over 70,000 pumps installed worldwide. We have manufacturing plants in 5 continents, 1, 2, 3, 4, 5 continents. So truly global presence. We are in all the markets that you guys are in: oil and gas, chemical, industrial, power, and water. And here is a brief overview of the pumps that we make. It's a complete range. We have the overhung pumps, foot-mounted, centerline, ANSI, ISO, general purpose, or API 610. Between bearings pumps, axially split, radially split, API. We have multi-stage pumps, again, axially split, and the radially split double case pumps. An excellent range of vertical multi-stage pumps and single-stage pumps. Double case pumps, API and general purpose. Topping up that range, we have some positive displacement pumps, plunger pumps, a range of mag drive pumps, and we specialize in package systems. That's the end of the commercial. Now back to the subject matter. This seminar is going to look at the impacts of curve shape, head rise to shutoff, and the new trend towards zero tolerances on equipment selection, reliability, and pricing, as well as the impact on downstream equipment. Ideally, we'd have a Q&A session at the end, but unfortunately, the Zoom type format doesn't make this easy with so many attendees. At the last count, we had, let me see, 110 registrations on this session alone. We had 220 on this morning's session, and also for each of last week's sessions. So it's hard to do it face-to-face. I'd encourage you to use the Q&A section at the bottom to ask any questions or make any comments that you have. I will address as many of them as I can after this session has finished, and we will certainly answer them by mail in the coming days. We are recording this session and we'll make it available to all attendees both as a YouTube link to the video presentation, as well as to a PDF version of the slideshow. We manufacturers are facing 2 problems on an increasingly frequent basis. Firstly, the fact that an increasing number of project specifications, or client specifications, are either assuming or sometimes specifying a head rise to shutoff of as little as 10 to 15%. Secondly, many specifications, especially those for transfer or loading services, are specifying zero negative tolerance on TDH. Their concern is in trying to meet the contractual guaranteed output flow in the event of a negative tolerance on the TDH condition. They're worried they won't meet their guarantees. These can seriously impact the design and price of the equipment and of downstream equipment. We will show you the impact of these on equipment selection, reliability, price, and on downstream equipment. So let's start with what API 610 says. It defines the pressure rating of the pump casings. It says the maximum discharge pressure shall be the maximum suction pressure plus the maximum differential pressure that the pump is able to develop with the furnished impeller, the rated speed, and the specified normal SG. So this means shut-off head with the rated impeller. In 6.3.2, it gives you options for using the maximum specific gravity in this calculation, and quite frankly, that is the usual case. Most specifications require it on the max SG, and I agree with that. You also have the option to do the calculation with the max diameter impeller instead of the rated impeller. You don't see that very often, I must admit. And the option is there for calculating it at the trip speed. And this would be applicable if you had a steam turbine driven pump. So the MAWP shall be at least the maximum discharge pressure as calculated here, plus 10% of the maximum differential pressure. Now this 10% margin, that's intended to accommodate the future head rise by fitting a larger impeller, i.e. 5% head rise by fitting a larger impeller in the future, and higher speed if it's a variable speed pump, and the testing tolerance per this paragraph. Here is what 8.3.3.3b, table 16 has to say. Rated point, the tolerance is plus or minus 3%. Shut off, it's 10, 8, or 5%, depending on the total head. The power tolerance is 4% plus 4%, and this tolerance encompasses loss of efficiency and loss of head. So it's a combination, 4%. So what does zero negative tolerance do to us? API 610 allows tolerances on rated head, shut-off, and rated power, and it does it for a very good reason. Because that is the reality of manufacturing. Semi-engineered pumps aren't built from investment castings, and variations between batches of castings is inevitable. Also, it's impossible to accurately measure shut-off head. In most test stands, the test engineers will take the flow back as far as they can to get a reasonably accurate reading, and then they'll extrapolate it the rest of the way. As you approach shut-off, the pressure gauge just wobbles and pulsates. It's impossible to read it accurately. So that's why they take it back as far as they can, get a decent reading, and then extrapolate it back the rest of the way. And this is, of course, one major reason why the test tolerance at shut-off is greater than it is at rated flow. So what will happen if you impose zero negative head on us? Instead of quoting per API 610 with a tolerance of plus or minus 3%, we will quote a tolerances of minus 0 plus 6, because we still need that 6 points of 6 percentage points of safety margin to be able to manufacture the pumps. And correspondingly, the shut-off head will go up by the same amount. Basically, what we've done is move the whole curve upwards. This, of course, impacts max allowable working pressure and the rated power. So what will happen if you impose zero positive power on us? Well, it just means we're going to quote 4% higher as the guaranteed power. We need those tolerances. Manufacturing needs tolerances. So how much is the head rise to shut off of a pump? What should you be allowing? Here's the golden rule. Do not assume 10%. This is seldom achievable except on very small process pumps. Typically, you'll find it's in the region of 115 to 130% for most pumps. Vertical pumps, VS1s and VS6s, it's more likely to be in the region of 140 to 150%. So if you assume 10%, you're in trouble before you started. Now, when pumps are in parallel operation, API 610 requires a 10% head rise to shut off. We recommend at least 15% is better. The steeper the curve, the more controllable pump operation is. Here is why. Here we see two curves, two HQ curves, a steep one in red and a shallow one in blue. A small change in head will have far less impact on the flow with a steep curve than it does with a shallow curve. So a 3% negative tolerance on head will have much less impact on flow if you have a steep curve. Similarly, small changes in the system head from the predicted head, i.e. the TDH that the system is actually demanding in the field rather than the calculated value. Small variances in that will have much less impact on flow if you have a steep curve. So what max allowable working pressure should we be specifying for downstream equipment? Well, you should start with the rated differential pressure. Assume a 30% head rise, unless you know otherwise. If you've got a pump curve that someone sent you already, then of course go with that. But if you're working in the dark, assume 30% or 50% if it's going to be a VS1 or VS6 pump. Add your 10% margins. Add your maximum possible suction pressure. Note, not the suction side design pressure. You might well be designing that for, say, 19 bar when the maximum possible suction pressure is only 4 or 5 bar. If this calculation brings you close to a flange break, 15 bar, 45 bar, 90 bar, or 135 bar, then you know, consult pump vendors to get more accurate figures to recheck your calculation. Do not specify zero tolerances because we can't do it. Or if you have no choice, it's been imposed on you by your client, then discuss the implications and options with the pump vendors. Incidentally, these pressure ratings are all based on A216 WCB steel or A105 steel plate at 150 degrees centigrade. If you're going to be higher temperature or different materials from this, you obviously need to adjust those figures. So let's look at some real world examples. Here is one I was personally involved in, and I've sanitized this to protect the guilty. It was a pump on LNG send-out duty, 411 cubes at 2212 meters of head. With this pump, it had 118% head rise to shut off. With this pump and API tolerances, the max allowable working pressure was 150.4 bar. Now, this is the selection that I tabled at the feed stage, right at the very beginning, and told them what the head rise would be and what the max allowable working pressure was going to be, about 150 bar. The PMC, however, had assumed a 10% head rise to shutoff with 0 positive tolerance on the shutoff head. And he set a downstream pressure rating of only 130 bar. 130 bar when we were telling them it was going to be 150 bar. Unfortunately, the EPCs weren't listening to us and they didn't pass it on to the client. So we're at the final pre-award meeting and we find that it still said 10% head rise, 0 positive tolerance, but it gets worse. To ensure parallel operation, they had insisted on 0 negative tolerance on shutoff head as well. So not only did we have to achieve a 10% head rise to shutoff, which we couldn't do because we were at 118, but it had to be exactly 10% head rise. Nothing, couldn't be higher, couldn't be lower. Exactly there, no negative tolerance, no positive tolerance. Well, we went away from that meeting overnight and came up with a compromise solution. Here is the pump we came up with overnight. We managed to get the head rise to 110%, but we still needed manufacturing tolerances. We still needed plus or minus 5% on that. So that took his max allowable working pressure to 136 bar. Remember, he wanted 130, and ideally we wanted 150. This selection, it's away from BEP. It has lower efficiency. Rated and max power are significantly higher. And the motor rating significantly higher as well. Really not a good situation. It was going to cost a lot more money. Mercifully, we lost this order in the commercial negotiations, so we didn't need to build this impossible pump they were demanding. Here's another example of how to get it wrong. Here we have the perfect pump. Right on best efficiency point, nice high efficiency, 80%, head rise, 135%. Actually, this is a vertical VS6 pump, so 135% head rise is actually quite low. It's quite good. It could easily be 140 or 150%. But the EPC had specified a max head rise to shutoff of 120%. And he specified 0 negative tolerance on the rated head. So this meant that we shifted the curve up. We quoted a tolerance of -0 +6 instead of plus or minus 3. And this had the knock-on effect of increasing the shutoff head tolerance to -2 +8 instead of plus or minus 5. So the max allowable working pressure did go up from 39.2 to 40.4. That wasn't such a big deal on this occasion. It didn't take you into a different flange rating, at least. So again, we went away and we looked for an alternative pump, and we came up with one, and here it is. The compromise selection. It's the next frame sized up pump. Big price impact. The rated point is at 85% of best efficiency point flow. So we're just within the preferred operating range, whereas before we were at 99% of BEP flow. Efficiency is 3.5 points lower. The power is 27 kilowatts higher. And the motor rating is 37 kilowatts higher. Head rise, 122%. They wanted 120%. It's still okay for parallel operation. We thought we might be able to get away with this. And quite frankly, an inexperienced engineer would be tempted to say, hey, that's an acceptable compliant selection. You know, you're within the preferred operating range and the head rise was 122%. Yeah, that looks okay. but he'd be wrong. And here is why. To explain it, we'd like you to understand the concept of shockless flow. This is the flow rate at which the flow into the impeller impinges on the inlet vanes at the optimum angle. It's normally close to the BEP flow of the full diameter impeller. Now, trimming this, the impeller has no impact on the shockless flow rate, because it is decided by the inlet geometry to the impeller, not the outlet geometry. Onset of suction recirculation is generally around 40 to 60% of this shockless flow rate. So the rated duty point might be at 85% of BEP flow, but it's at 65% of the shockless flow. This selection's a train wreck waiting to happen. It's probably okay on a small, low energy pump. I mean, it will be okay on a small, low energy pump, a 2-inch or 4-inch pump at 6 to 8 kilowatts, but definitely not on a multi-stage 350 kilowatt pump like this one. I would advise you to avoid selections near the minimum diameter on medium and large pumps. And if you must select close down, if you're forced to select down there, make sure that you select to the right of BEP. Here is illustration from Karasik of suction and discharge recirculation. Note that suction recirculation is not impacted by impeller diameter. It's solely down to the inlet geometry of the impeller. Discharge recirculation is trim dependent. As this gap gets bigger, there's more recirculation. Well, that pretty much finishes session 2. I hope I've been able to get across to you the importance of the following 6 key requirements. Start with the rated differential pressure, max SG. Unless you've got a curve that shows you something different, assume a 30% head rise, or 50% if you're a VS1 or VS6 pump. Add your 10% margin per API 610, 635. Add your max possible suction pressure, and that gives you your max allowable working pressure. If it is close to a break between flange ratings, consult the pump vendors to get more accurate shut-off head predictions. Do not specify zero tolerances, or if you're forced into it by your client, discuss the implications and possible options with the pump vendors. Coming attractions. The next of these seminars we're planning is on Thursday, the 3rd of June, and it's going to be the importance of using system curves in pump selection and successful pump operation. Again, there'll be 2 sessions, one for the Eastern Hemisphere and one for the Western Hemisphere. That's you guys. The invitation will be published very soon. Put it in your diary. You'll be getting the invitation in the next few days. Future sessions are planned. These are what I have in mind at the moment. But I would welcome your input as to subjects that you would like us to cover. Again, any comments that you might have or questions you might have can be addressed in the Q&A comment section, and we'll answer it either in the coming few minutes, or we'll do it over the next few days. Otherwise, if you think of something later, please don't hesitate to contact us by phone or email to your local sales office or to info rawpumpen.com. Well, that's the end of the slideshow. I'm going to open it up for a Q&A session. I mean, our marketing team are standing by to direct your questions or suggestions to the right people. I'm going to leave it open so that you questions that you post in the Q&A box, I will endeavour to answer now, or if they can be done briefly and concisely now. Otherwise, we'll do it in a full answer in the coming days. Thank you again for attending today. I enjoyed preparing and presenting it. I hope you found it useful. You will be getting, in the next few days, you'll be getting a survey, a very brief survey, and I'd ask you, please take the time and fill it in. It's only a very brief one. Your feedback will help me improve the next sessions. And as I said, the next session is on the 3rd of June, which is 2 weeks today. Look forward to seeing you for that one. Now let's have a look at a couple of Q&As here. Let me just see what we have. Thank you. I have one from John Marker asking for a copy of the slides. Yes, anyone who is registered for this or any of the attendees today, you will automatically get a link to the YouTube video of this, and furthermore, you'll get a PDF copy of the slides. Dylan Cottingham has said, is approaching the 40 to 60% of shockless flow range as damaging of a parameter when dealing with water pumps as well? Is this a factor that comes into more importance when the fluid viscosity is greater? I'll need to think about the fluid viscosity, but certainly for the point of view of water pumps, yes, it is very definitely the case. In fact, it could be more so. When you think water has a specific gravity of 1, so any shocks are that much harder to accommodate than when you're talking about a light hydrocarbon with SG of 0.5 or 0.6. Clearly, the damage could be far worse. So yes, it's something to be avoided. How does using a VFD affect shockless flow? Really, it doesn't. The shockless flow is the full diameter of the full speed, full diameter impeller. So changing the speed is really the same as changing the diameter of the impeller. It hasn't affected how the flow goes into the impeller. I can give you a better answer than that, a fuller answer than that, but that's the brief answer. I will give you a more detailed answer as a written response. Abdul Qayyam has asked, can we ignore velocity and velocity head in pump curve calculations? How much is it going to affect our curve? Yes, to a large extent you can ignore it because it's already been taken into account when we drew up the curve in the first instance. So it's not something that you need to take into account again. It has already been built into the performance curve that you get. Abdul Qayyum has asked, may we put 2 pumps with different flow into a common header? I think that needs a more detailed answer. And in fact, I would ask you, Abdul, to send us through the example that you've got in mind so that we can address it properly. There are clearly quite a few aspects to be taken into account when you're feeding 2 pumps into a common header. The 2 pumps effectively be trying to work in parallel. Perhaps, it depends on your piping configuration, but you could be asking them to effectively work in parallel, and they are different pumps. Yugen Ijada has said, can you copy others on that written response about VFD and shockless flow? Yes, I will. You will all get the answers to these questions. Josh Easterbrooks says, if you have a large multi-stage pump that has been in service with a near maximum impeller, and you want to repurpose the pump to fit another application, this application has different head and flow requirements that seem to be met with trimmed impeller that will be relatively close to the rated minimum impeller diameter. Should there be any concern given to the concepts presented here? Good question. Any re-rating of a pump wants to be carefully considered. What we are able to do, for example, is take a completely different impeller, a low flow impeller from a completely different pump, fit it inside the volute of your existing pump with some adjustments to the volute, possibly fitting an insert in there. So you effectively have small pump hydraulics in a big pump casing. These are the sort of things that we, and not just Ruhr Pump, and other vendors can do this as well. So that is definitely the way to go. Discuss it with the manufacturer of the pump and get them to give you a low flow kit effectively. Just looking to see if there are any others here. There's some in the chat that I think have already been covered. Yes, I think that's covered everything. I don't see any more, so is there another one here? Yes, another one from Abdul. Will the two parallel pumps give any effect back on their performance if they are with different flow rate and joining a common header? In my last week presentation on API 610, I did address pumps operating in parallel and how the important thing is that the two pumps should have very close matching curves. That's the key thing to good operation, an equal sharing of the load. Two different pumps with different flows, if they're in parallel operation, you're going to have to be very careful with flow metering and of each pump to make sure that they are sharing the load proportionately to their size. I will give you a better answer than this in writing. It's difficult to explain that to you right now. One more question here from Martin Della Torre. If I have a service that has a maximum suction pressure that is larger than the rated differential pressure, how can it affect the shutoff margin limitation? Because maybe the margin will be greater than specified by client. I don't fully understand the question. I need to think about it, I'm afraid, Martin. I have a service that has a maximum suction pressure that is larger than the rated. I don't see how you can have a maximum suction pressure larger than the rated. Okay, very high suction pressure pump, greater than the differential pressure. Well, when you calculate the downstream max allowable working pressure, it's going to be worked on the differential pressure of the pump plus the maximum suction pressure. So that very high suction pressure would have been taken into account in calculating the max allowable working pressure. Okay, I don't see any more questions. Oh, sorry, somebody has come back. Dick Shear has said, can a low flow kit be used for initial flow and then later removed for larger flow? The answer is yes, if it was designed that way in the first instance. If it was designed to be reversible, yes. You have to be careful when you ask the question, yes. Okay, I think that's all the questions. Oh no, here comes another one. Do we have any additional consideration when we use VFD, says Oscar Escobar. Not really, not in the terms of establishing the max allowable working pressure. API 610 already takes that into account when it has the 10% margin. It allows for the overspeed condition or the increase in speed. You'll probably, with a variable speed pump, you'll probably use a full diameter impeller because you can get your extra 5% by speeding up the pump by 2 or 3%. Later if you need to do so. So that's the advantage of a VFD. You don't have to change an impeller. You can just crank up the speed a little. Amaya Popali says, if I have one pump with a set design point and corresponding shutoff head, and I want to maintain that shutoff head, but increase the design point, i.e. have the same flow but at a higher head, is it doable? Probably not. It might be possible with a different pump design. You might need to use a different pump hydraulic, and we might still be able to maintain the shutoff head. But fundamentally, if you take the same pump and just put a larger impeller in it, you're just going to take the curve and move it up like that. So your shutoff head will go up by a corresponding amount to your design point. Eric Moray has said, when we trim the impeller, the pump head goes a little bit down from the theoretical one. That's due to the recirculation that occurs at the gap between the case and the impeller. Well, when we trim the impeller, you will automatically get less head. It's the centrifugal force that's occurring. If you've got a smaller diameter impeller, it will be generating less head. Yes, you will get a certain amount of recirculation, so the efficiency will be ever so slightly less than it is with a full diameter impeller, say. And you will see that quite commonly. As you trim an impeller, its efficiency goes down a little. And part of that is due to discharge recirculation. We have an anonymous attendee who has asked, what would the fundamental considerations be for pumping in series? That is a whole different presentation, and it's one I'll be covering in a couple of weeks' time when I'm going to look at system head curves and their impact on the pumps. So yeah, sign up, Mr. Anonymous attendee, and you'll learn a bit more about that in 2 weeks' time. Okay, I think that's all the Q&As we've got at the moment. So again, thank you very much for attending today. And I look forward to seeing you guys in 2 weeks' time, 3rd of June. Bye-bye.